It's about a star, the 10th most brilliant star in the night sky. It has a name that I won't be sufficiently valiant to attempt and articulate. However, you could, clearly. It's become half more splendid as the universe is getting bigger. In 1929, researchers observed that our bodies are made of chemicals formed in the cores of stars. This is 1957. The sky isn't just beautiful to look at, it shows us how incredibly strong our universe is. There is so much happening in the universe that, most of the time, we don't know what's going on. What are we doing here? Why are there planets and stars? What else could there be? We don't pay attention to things until they get really bad, even if they will ultimately affect us too. That might have happened with Betelgeuse. Betelgeuse has forever been one of the biggest stars in the sky, but now it started shaking severely, which implies something very unsettling is happening. Join us as we tell you everything you need to know about Betelgeuse and how it might impact our future, too. Betelgeuse isn't like other stars. It never has been. It's one of the biggest stars ever discovered and, unfortunately, makes our sun look small, with a mass around 20 times that of the sun. Betelgeuse is obviously a very giant star. However, perception isn't always correct. From where we are, Betelgeuse might look like just another faraway star, but it has a much higher rank than that. This distance, more than 640 light-years from Earth, may not seem significant at first, but in space terms, it's enormous. This means that even if we could move faster than light, which is currently impossible, it would still take over 640 years to get from here to Betelgeuse. Under normal circumstances, it would take more than 12 million years to make the connection. That's longer than all of humankind's history on Earth. That really makes you think about how powerful just one star can be. It has been intensely shaking since then. Stars may seem like calm things in space that are just there, no matter how big or small, but this one shows that it's not true. Researchers don't know what the sounds mean. As you can see, Betelgeuse has never been still. It's been called a pulsating red supergiant for a long time, and it changes constantly. There's a difference between how bright the star looks when it's expanding and how faint it looks when it's contracting. These changes in brightness happen over long periods, from 10 to many days. Another interesting thing about Betelgeuse is that its brightness changes a lot. It goes from about plus 2.5 magnitude to a brighter 0 magnitude, which is a huge difference for stars. These changes in brightness actually occur in cycles. The shortest cycle lasts around 185 days, and the longest cycle lasts about 2,335 days. There are times when these changes happen more consistently and in a way that can be recorded. The name for this effect is V-band magnitude. In February 2021, its V-band value of plus 1.614 was one of the lowest it had been in recent years. This was different from Betelgeuse's usual brightness, even though it was still quite bright. Betelgeuse's significance isn't just shown by how its brightness changes. Its bright red color comes from having a surface temperature of around 3,500 Kelvin, which is much cooler than the sun's 5,500 Kelvin. Since we just said that the sun is smaller than Betelgeuse, that might seem odd at first. However, it is consistently brighter. It will be the exact opposite of our sun now that it's cooler. Due to the cooler temperature, less energy is emitted per unit of surface area, making it appear dim. It's one of the largest stars we know of, yet it has generally been a stable star, even though it's a pulsating giant. But what could have caused the current shift from calm to storm? That's where things get more complicated. People often say it's because Betelgeuse's gas shell is on fire. Betelgeuse is slowly running out of hydrogen in its core through nuclear fusion, turning it into helium as it progresses through its star life cycle. This is what you'd expect from a red supergiant like it. As hydrogen fusion slows down in the star's core, the upper layers expand, making the star bigger. This stage marks the beginning of the star's transformation into the red giant phase. At this stage, helium builds up in a shell around the core, which is now mostly hydrogen. This helium-rich shell's high heat and pressure start a second nuclear fusion process called helium shell burning. Helium particles start to fuse, creating heavier elements like oxygen and carbon. This process emits energy that pushes against the force of gravity, which is trying to pull the star's outer layers inward. A helium shell burst isn't as steady as hydrogen fusion in the core. It can cause energy to build up and then release at regular intervals, sending things in an unusual direction. These changes in the amount of energy a star emits can make its structure less stable. When more energy is created, the outer layers expand. When that energy is released, the outer layers contract. These oscillations of expanding and contracting appear as pulses, which change Betelgeuse's brightness over time. When helium shells burn, they release a lot of energy that can cause strong stellar winds, especially in red supergiant stars like Betelgeuse. A lot of mass can be stripped from the star's upper layers by these winds. These stellar winds cause stars to lose mass, which significantly affects how matter and energy are distributed within the star and influences its evolution even more. Like regular breaths, the outer layers pulse outward when the shell grows and inward when it contracts. There's a steady rhythm that we see as changes in the star's brightness. It's like the star's heartbeat. Even though this might be what's happening, there are still things that need to be done to be certain. Astronomers use various techniques to understand what stars like Betelgeuse are doing when they pulse. Photometry and spectroscopy are two of the most important ones. Each sheds light on a different part of the problem. Astronomers carefully observe how the star's brightness changes over time using photometry to do this. To record how much light the star radiates at various times, Betelgeuse throbs, which causes changes in brilliance, assisting us with understanding what is happening under these changes. This technique gives researchers an immediate connection to the star's changing behavior, allowing them to monitor the subtleties of its light output. However, spectroscopy provides a more complex picture. By analyzing the star's light at various frequencies, this method reveals important details about the star's temperature, composition, and movement. When Betelgeuse pulsates, its spectral lines shift and broaden, letting us see conditions within its outer layers. By studying these changes in its spectrum, we can learn more about the processes causing its pulsations. Using these techniques together allows researchers to construct a full narrative of how a star's pulsations behave. The data gathered from measuring luminosity with photometry contributes to insights gained from spectroscopy and spectral analysis. Astronomers can piece together how changes in the star's brightness relate to its internal processes. By using both methods, they gain a fuller image of Betelgeuse's pulsational rhythm. Astrophysicists take an additional step to delve into the star's interior by using computer models to simulate how the star functions and moves internally. These models incorporate many elements, from the equations governing stellar structure to the complex interplay of nuclear processes and fluid dynamics within the star's core. Through these simulations, they can observe how Betelgeuse changes and how its pulsations evolve with shifting conditions. This approach brings theory and observation closer, especially in understanding what's happening on the surface of a throbbing star. But that's not all there is to it. Stellar convection is a fascinating process that can occur deep within the hearts of stars like Betelgeuse. The energy produced in the star's core moves to the surface through this natural process, which maintains the balance between the star's internal processes and its external glow. Stellar convection involves the movement of matter within a star due to temperature changes. A large amount of heat is produced at the center of the star, where nuclear fusion occurs. The material surrounding this heat source becomes hotter and less dense, expanding and rising to the top of the star. Simultaneously, cooler material from the star's surface sinks closer to the core. The upward movement of hot matter and the downward movement of cool matter form convection currents, transferring energy from the star's core to its outer layers. This convection process changes the star's surroundings over time. As hot matter rises, it carries energy, causing the star to appear even brighter because this energy is emitted as light when it reaches the outer layers. However, variations in energy flow, driven by the rise and fall of hot material and convection currents, lead to changes in the star's light output, causing pulsations. The star's brilliance fluctuates as the convection currents periodically move more or less energy. On the other hand, the pulsations might have an entirely different origin. In binary star systems, the movement of material can also affect the lives of stars. Mass transfer can occur in such systems, where two stars orbit each other due to their mutual gravitational pull. This interaction can result in the exchange of matter between the stars, which can have substantial impacts, such as initiating pulsations. Stars in a binary system orbit a shared center of mass. One star, called the donor, might approach its companion, the accretor, depending on their size and separation. Since the stars are gravitationally attracted to each other, matter can flow from one star to the other. As matter transfers from the donor to the recipient, significant changes can occur in the receiving star's structure and behavior. The added mass makes the receiving star heavier, altering its temperature, pressure, and nuclear fusion processes. These structural changes can lead to pulsations in the receiving star. The influx of matter disrupts its balance, causing instability that manifests as pulsations. The star's outer layers might expand and contract rhythmically, resulting in brightness fluctuations. The star is trying to find a new equilibrium between the forces affecting it, such as gravity, radiation pressure, and nuclear reactions within. These dynamics can greatly impact the evolution of stars in binary systems, changing everything for the recipient star and potentially guiding it down a different evolutionary path than it would have followed alone. Historically, researchers often viewed stars as individual celestial bodies, even when they were supergiants like this one. Many did not study how stars interact with each other, let alone how they exchange energy. But such exchanges have been occurring for millennia throughout space. Now, we have telescopes and research teams capable of using all available data to unravel what has been happening in our universe. One potential reason for Betelgeuse pulsations has garnered attention: the possibility of an impending supernova, which would cause the star to explode and destroy everything in its path. Like many other massive stars, Betelgeuse is nearing the end of its life cycle. Throughout its existence, it has maintained a balance between gravity and nuclear fusion within its core. However, this balance will not last forever. Gravity, which exerts a strong force on Betelgeuse's massive interior, pulls inward. At the same time, nuclear fusion processes in the star's core fight against gravity. In these fusion reactions, lighter elements like hydrogen are converted into heavier ones like helium, generating immense amounts of energy that exert outward pressure. It is believed that this equilibrium keeps Betelgeuse stable, preventing it from collapsing under its own weight. Over time, as Betelgeuse consumes its nuclear fuel, the balance between gravity and fusion gradually shifts. The decreasing availability of hydrogen fuel affects the star's energy production, reducing the outward pressure. Consequently, the core begins to contract due to gravity's pull. As the core contracts, its temperature rises due to the compression of matter. This temperature increase results from the core's contraction, as particles within the core move more rapidly. The higher temperature initiates a new phase of nuclear fusion, which is more intense. The core becomes hot enough to fuse heavier elements like helium and carbon, producing even heavier elements and releasing energy in the process. This fusion of helium and carbon marks a shift from the star's earlier hydrogen fusion-dominated phase. As fusion progresses, elements continue to combine, forming increasingly heavy elements, ultimately leading to the formation of an iron core. Iron is unique because it requires more energy to fuse than it releases, marking a turning point in the star's life. Stars advance in a way that the formation of an iron core disrupts the energy balance that had been maintained by previous fusion reactions. Fusion of iron does not generate a net release of energy, causing the core to lose its ability to create sufficient outward pressure. Eventually, gravity wins, and the iron core collapses in on itself. The gravitational collapse of Betelgeuse's iron core at this point would trigger a significant and explosive event known as a supernova. During this catastrophic event, the outer layers of the star are violently ejected at phenomenal speeds, resulting in a massive release of energy. For anyone observing the star from afar, they would see bursts of light throughout the sky. This collapse produces a huge shockwave that races outward from the core, affecting the star's outer layers with extraordinary force. The energy of the shockwave is so immense that it can easily tear apart the star's structure, throwing its outer material into space at unimaginable speeds. The energy released during a supernova is staggering, often rivaling the brightness of an entire galaxy for a brief period. This event can outshine countless individual stars in the surrounding area. The resulting burst of light and radiation is not only visually captivating but also scientifically valuable, providing insights into the extreme physical processes occurring during a star's final moments. Currently, Betelgeuse is approximately 600 light-years from Earth, which means that a supernova would be visible to us. We'd see our entire night sky brightened, and the effects could last for a few days or even weeks, depending on how the supernova unfolds. But what if it were just a bit closer? In that case, things would take a turn from a beautiful light show to an absolute disaster. Gamma ray bursts are among the most energetic and intense phenomena in the universe. They can be associated with certain types of supernovae, particularly those involving massive stars. A GRB is a burst of high-energy gamma-ray radiation emitted due to extreme astrophysical processes like the collapse of massive stars or the merging of compact objects like neutron stars. If Earth were to experience a direct and intense GRB from a nearby supernova, it would affect everything. Earth's ozone layer is a protective shield in the stratosphere that absorbs and filters out a significant portion of the sun's harmful ultraviolet radiation. A strong GRB could disrupt the ozone layer, leading to its depletion. The intense gamma-ray radiation could break apart ozone molecules, O3, reducing the concentration of ozone molecules in the stratosphere. This depletion would weaken the ozone layer's ability to block UV radiation. With a compromised ozone layer, more ultraviolet radiation would reach Earth's surface. UV radiation can have harmful effects on human health, causing skin damage, increasing the risk of skin cancer, and affecting the immune system. It could also harm marine life, terrestrial ecosystems, and plant growth, leading to ecological disruptions. And humans aren't safe here either. Increased UV radiation levels due to a weakened ozone layer could lead to higher rates of cataracts in humans. Increased UV exposure could also suppress the immune system, making people more vulnerable to various diseases. Elevated UV radiation could affect crop growth and agricultural productivity. UV-sensitive crops may suffer reduced yields, altered growth patterns, and lower nutritional value. This could have devastating implications for global food security. But even if we consider this on a more superficial level, there are things that might initially seem like minor inconveniences but wouldn't be. The intense radiation emitted during a nearby supernova, such as one originating from Betelgeuse, could have a significant impact on Earth's technological infrastructure through the generation of electromagnetic pulses, EMPs. These EMPs are bursts of electromagnetic energy that can disrupt or damage electronic systems, communication networks, and power grids. The sudden influx of electromagnetic energy from the supernova-induced EMPs could overload and disrupt sensitive electronic devices. This could include everything from consumer electronics like smartphones and computers to more critical systems like satellite communication equipment and medical devices. This means that if there are any medical emergencies, reaching and accessing healthcare services would become increasingly difficult. One of the most concerning aspects of EMPs is their potential to impact power grids. The electromagnetic energy could induce currents in power lines and transformers, leading to equipment damage or even complete shutdowns. This could result in widespread blackouts affecting homes, businesses, hospitals, and other essential facilities. But it goes much deeper than that. The interconnectedness of modern technology means that EMP-induced disruptions could have cascading effects on financial systems, transportation networks, emergency services, and other critical infrastructure, potentially leading to a breakdown of essential services. Until the effects of the supernova subside, the entire Earth would essentially have to remain on pause, and that could easily take years. What's even worse is that some of these impacts extend beyond direct physical effects and influence Earth's atmospheric and climate dynamics. The influx of energy and radiation from the supernova could disrupt atmospheric dynamics, potentially leading to altered weather patterns. Changes in atmospheric circulation could result in unexpected weather events, such as shifts in precipitation patterns, temperature anomalies, and even large storms that appear suddenly in various regions worldwide. The energy released during a supernova could also introduce additional heat to Earth's atmosphere, leading to short-term temperature variations affecting global climate stability. Nearby, worldwide temperature changes could affect ecosystems, agriculture, and other sensitive environmental systems. High-energy particles and radiation from a cosmic explosion could interact with Earth's atmosphere, leading to adjustments in atmospheric chemistry. This could include changes in the composition of certain molecules and compounds, indirectly impacting climate and air quality. Given how severe climate and air conditions are in most parts of the world, even a slight push could worsen the situation. If food shortages don't hit us first, the altered weather and temperature fluctuations could impact agricultural production. Sudden shifts in temperature or precipitation could affect crop growth, yield, and timing. These disruptions could also be disastrous for food security and supply chains, which would already be impacted by the UV rise. Whole ecosystems could experience temporary disturbances due to rapid changes in environmental conditions. Species reliant on stable climate patterns and seasonal cues could face challenges in adapting to sudden shifts, potentially impacting wildlife behavior, migration patterns, and reproduction. If these aftereffects last long enough, some species could be entirely wiped out. It's easy to forget that we're affected not only by what's happening on Earth but also in nearby space. The explosion of a massive star, like Betelgeuse in close proximity, could have significant consequences. The acceleration of cosmic rays, high-energy particles originating from space, presents a radiation risk to astronauts traveling in space. A nearby supernova explosion could increase the number of cosmic rays in space environments, raising the risk of radiation exposure for astronauts. This poses a challenge for extended missions like those to Mars, where astronauts would be exposed to elevated radiation levels for extended periods. Cosmic rays carry enough energy to interfere with electronic components in satellites and spacecraft. These high-energy particles can collide with sensitive electronic equipment, potentially causing bit flips, data corruption, or even hardware damage. The increased flux of cosmic rays resulting from a nearby supernova could heighten the risk of these electronic disruptions on a wider scale. Heightened cosmic ray activity could also affect astronomical observations conducted from space-based observatories. High-energy particles could interfere with detectors and sensors, potentially impacting the accuracy of data collected from these observatories. But there's more. Stars often don't just go supernova, they can also transform into black holes. This process involves the core collapsing beyond a critical density, known as the Schwarzschild radius, where gravitational forces overpower all other forces, causing the star to effectively collapse in on itself. Betelgeuse's massive mass and gravitational influence would become concentrated within an incredibly small volume, leading to the formation of a singularity, a point of infinite density at the center of the black hole. Surrounding the singularity is the event horizon, a boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. If Betelgeuse were to become a black hole, its surface appearance to distant observers would remain relatively unchanged until interacting with the event horizon. Unlike a supernova, which produces a burst of light and energy, the formation of a black hole might not result in an immediate visible event. Rather, the transition could be relatively subtle, almost silent in a way. However, if it occurred close to us, things wouldn't be so quiet, they'd be catastrophic. For starters, the gravitational pull of the forming black hole would unleash extreme tidal forces on surrounding objects. These tidal forces would be far stronger than anything experienced on Earth. Nearby planets, moons, and asteroids could be torn apart or disrupted by the intense gravitational gradient, leading to fragmentation and potential collisions. The immense gravitational force of the black hole would disturb the orbits of nearby celestial bodies. Planets and other objects in the vicinity could have their orbits altered, potentially leading to chaotic paths, collisions, or, in the most extreme scenario, ejections from the solar system. As Betelgeuse collapses into a black hole, surrounding matter could be drawn toward it, forming an accretion disk. This disk would heat up and emit intense radiation across the electromagnetic spectrum, including X-rays and gamma rays. The radiation could damage the atmospheres of nearby planets and significantly impact any life forms or ecosystems. The formation of a black hole involves the release of high-energy particles and radiation, which could pose a threat to technology, satellites, and even spacecraft passing through the area. Sensitive electronic systems could be disrupted or damaged by the intense radiation generated during the transition. The gravitational field of a massive black hole is immensely strong due to its extreme density and compactness. If a black hole were to form from a star like Betelgeuse in the vicinity of our solar system, its gravitational influence could significantly impact the orbits of distant objects, such as planets, asteroids, and comets. The gravitational force exerted by the black hole would pull on nearby objects, altering their trajectories and potentially causing them to stray from their original orbits. The delicate balance of the solar system's orbital dynamics depends on the gravitational interactions between its various components. Planets, for example, follow stable orbits around the Sun due to the Sun's dominant gravitational pull. However, that doesn't mean nothing can ever happen to it. The presence of a large black hole nearby could disrupt this balance. The reconfiguration of orbits caused by the black hole's influence could lead to objects being flung out of the solar system, colliding with each other, or even falling into the black hole itself. Orbits that were once predictable and stable could become erratic and chaotic under the strong gravitational forces of the black hole. Moreover, the alteration of orbits could have ripple effects throughout the solar system. Changes in the positions of planets and other objects could affect gravitational interactions, impacting the overall stability of the system. While the Sun's gravity would still play a significant role, the introduction of a massive black hole could introduce new gravitational interactions that were not present before, leading to a destabilized solar system, which, in simpler terms, just means a complete breakdown of life as we know it. But the good news is, Betelgeuse isn't right next to Earth. It sits at an extremely far distance, meaning that, in all likelihood, when the star goes supernova or ends up turning into a black hole, most of us won't even know what's happening until things return to normal. So, what do you think? Would it be a spectacular supernova light show or a catastrophic black hole? Let us know in the comments below. If you enjoyed this video, please give it a thumbs up, and as always, we'll see you in the next one.